Hello, everyone. My topic is the journey to achieve 1000 TPS for a real-world core banking application. I'm Sidney Chen from PinCap. At the abstract, we all know performance tuning is complicated, especially with distributed database like TiDB. It becomes more challenging when the whole system on ARM64 servers. In this session, we will share how to achieve 1000 TPS for core banking application. And we will show how to apply general methodology to identify the bottleneck, how we explore various tuning techniques, such as improving the CPU memory affinity and slow query optimization. And we believe that these methodology and techniques can be easily acquired by common database users. A little bit about myself. My name is Sidney Chen. I'm a performance engineer at PinCap. Currently, I'm responsible for building the infrastructure for TiDB performance testing. I also involved in many real-world customer cases to help their users to get the maximum performance out of TiDB. The agenda, we are talking about user response time versus database time. And then we will go through a real-world story. We will show how to do circuit tuning, how to improve the Numa affinity, and talking about one of the key features, prepare plan catch, and the optimized change to stabilize the execution plan. And finally, we will show how TiDB keep improving for the users to run mission critical OLTP. User response time is the total amount of time it takes to process a request. And then usually a user sends a request through the network to application. And the application processes the user request. During the process, it will interact with database multiple times, and then get back the response to the user. User response time usually includes the network latency between the user and the application, and the network latency between the application and the database. The blue one is that the time spent inside application, and the green one is that which we call database time. Is the database processing the request from the application. So it's very important that we get a full picture of user response time. Then we can know where is the bottleneck of the whole application system. Then we can take action to improve the performance. Otherwise, if we don't know where is the bottleneck, we can easily blame each other, each different component, and different organization can blame each other for the poor performance. So it's very important. We know where the time goes for the user response time, where is the bottleneck. Database time is total amount of time database process the application request. And we can drill down database time by different dimension. For example, in this case, database time is consists of the time processing different secure type, like the select, commit, update statement. And we can also drill down database time by different secure phase, like SQ, compile, get token. And there is multiple ways to compute database time in TiDB. For example, we can multiply QPS by the average query latency. We can also multiply average active connections by the delta T. And there's a promises metric to recording the database time. So what we just suggest is to do performance tuning by database time. We can compare the database time to user response time, so we can know if either the bottleneck is inside TiDB or outside TiDB. Okay. Okay, then we go to the real world case. This is a performance tuning project for a core banking application. We will show how to bring the TPS from 1 to over 1,000. The background, together with the application and hardware partners, we need to answer the question, how the application perform on open source distributed database like TiDB and on the new ARM hardware. We have 7 servers, 6 for the database, 1 for the application, and each server has 16 Numa. Each Numa has 8 cores and 16 RAM and 1 NVMe disk. The application connects to a database through HAProxy. HAProxy is deployed on one of the database server. We use the TiDB 5.1 version. The workload is actually really heavy. 66% of the statement is select, and 15% of the queries is write statement, either commit, insert, and update statement. So when we first run the application, it's very scary. The QPS is just 1. So it's not normal for an OLTP application. We first look at the TiDB dashboard. The QPS inside database is 150, very low QPS, and the 99% percentile latency is over 1 minute. There's a slow query, and there's actually application error complain that the coprocessor task timeout. And look at the slow query execution plan. It turns out that it is doing 4 table scan on the transaction history table. And it turns out that this is a missing index case. So after create a composite index on the multiple columns, it used the index range scan rather than 4 table scan. The second case, slow queries also doing 4 table scan. There's all predicate for the client relation table, and because index merge is disabled by default, so for every execution, the TiDB need to scan 50 million rows. So we need to enable the index merge feature manually by setting the global variables. After enable the index merge feature, we get the index merge execution plan. So the execution time is reduced to 8 milliseconds. The third execution is is related to the index merge. It's actually the same secure statement of the previous statement. We got two execution plan even after we enable the index merge feature. One, the back plan is average latency is 1.2 millisecond. So two execution plan. The faster one is use the expected index merge execution plan. The bad one is doing for table scan. But the strange thing is that for this execution plan, we see there's a limit operator, but we don't have limit expression in our secure test. Why? It turns out that the application set the secure select limit. So this is no limitation for the index merge feature. When the application set the secure select limit, they can use the index merge feature. So we solve this case by provide a whole fix to solve this issue, so that even the application set the secure select limit, they can also use the index merge feature. Okay, after solve these three kinds of slow query, the TPS is up to 30. So we increase the TPS from 1 to 30 by doing slow query optimization. The next one is that we review the cluster config. The current topology is have 3 PD, 3 TiDB, and 6 TKB. Each TiDB binding with 5 Numa. And we adjust the topology. We have 1 PD, 36 TiDB, and 6 TKB. Each TiDB binding with 2 Numa. Each TKB binding with 4 Numa. After the change, the TPS is up to 320. Then where is the bottleneck now? Because we see relative idle both on database server and application servers. For example, each TiDB instance used 100 to 500% CPU, and actually this means that each TiDB is using 1 or 5 cores, but each TiDB is finding 2 Numa. They have 16 cores, so TiDB has plenty of idle CPU resource. And application server CPU utilization is around 10%. So this is a very common situation that we can get more throughput from the system, but the system seems under very low CPU utilization. We can compare the user response time to database time. The user response time per second is 320 seconds. How do we get this number? We just multiply the TPS by the average transaction latency. And for the database time, the per second is 39 seconds. We can multiply TPS by average query latency. So we divide database time by user response time. The database time just takes 12% of the total user response time. So we know that the TiDB, the database is not the bottleneck. The bottleneck is outside of TiDB. We can identify the bottleneck by compare the database time to user response time, by actually require some math, some compute. Is there any easy way? The answer is yes. For TiDB, we have the query duration and connection idle duration metric. So the 80 percentile query duration is 3.8 millisecond. The connection idle duration, the 80 percentile is 25 millisecond. This means that TiDB, the connection inside TiDB spend 3.8 millisecond finish processing a query statement, and it need to wait 25 milliseconds to get another secure statement to process. So this is bottleneck is outside of the TiDB. So just compare the duration versus connection idle duration. We know the bottleneck is outside of TiDB. So we know the application server, both application server and the database server is very low CPU utilization. So where is the bottleneck? We look at the network latency between the application server and TiDB. So we run np state on the server which deploy the HAProxy. We find something very interesting. For the CPU 027, the first Numa is almost 100% busy. 100% busy. And there's around 40% on to 94% CPU is doing software IRQ. Why? Because for this hardware, all the network software IRQ is routed to the first Numa to keep the IRQ affinity. And remember, we adjusted the topology that the first Numa also run the TiDB instance. So this is why the user CPU plus the 6 CPU and the software IRQ CPU is the first Numa is 100% busy. Then we gather the frame graph on the whole system. There's around 20% of the CPU is spent on the system called finish task switch. So whenever you see very high CPU on the sys cores, it probably means that the system is running very inefficiency. The CPU is spent on the sys cores rather than on the application code. The next step is looking at the impact of the Numa, because HAProxy and the PD server is running without Numa binding. So there's high finish task switch for HAProxy. There's a high software IRQ entry, and the spin lock for PD servers. So this is the symptom that without the Numa binding, without the CPU and memory affinity, the system cost will consume lots of CPU resource. So we adjust the topology. We reserve the first Numa for just for the network software IRQ. We add the Numa binding for HAProxy and PD server. We double the number of TiDB instance. Each TiDB just bind with only one Numa. After the change, the connection idle duration reduced from the 25 millisecond to 5 millisecond. And because there is a more workload coming into the TiDB cluster, the TPS is up to 600. Then we see one strange symptom is that the total connection in TiDB is 2000, which match the session limit for the HAProxy, and the total connection is limited to 2000, and after that the MySQL cannot connect to the TiDB because it reached the HAProxy session limit. So we changed the HAProxy to multiple process mode. Then the total connection is up to 4,400. And we also explore other proxy solution in-house. For example, for the Java application, they can use the client-side load balancing. So the traffic between application and the TiDB does not need to go through the HAProxy. And we also explore, try the LVS. And it turns out that LVS NLT mode can reduce the connection idle duration time by 42%. So it can be a better option for HAProxy. We also fix some environment issues. For example, 3 server they does not have the NVMe disk mounted. So this means the 3 TiKV is running on hard disk rather than NVMe disk. And each server have 2 network cards. One is the 1 gigabit, the other is 10 gigabits, and the 3 TiKV use the long IP to join the cluster, which means they use the slow network card. The solution is to mount the NVMe for the TiKV storage, and we need to scale in to bring down the 3 TiKV, and then scale out to use the high-speed network card. So after the fixes, the TPS is up to 880, but seems the workload is very unstable. There's a response time spikes from the low runner dashboard, and we see TPS drop when the response time spike. So this is a very strange situation. We look at the database dashboard. There's also a small spike in the query latency. If we see 49 percentile duration, there is a huge spike. So this means that the spike in the application response time is caused by TiDB. So we check the system log and the TiKV metric. It turned out that it's caused by TiKV OOM. Why TiKV got OOM? Because when we scale in 3 old TiKV, we forgot to purge the tombstone, purge the old TiKV instance. So the memory is not released, which caused the 3 new TiKV OOM. So after push the 3 TiKV, and we run 15 scale application server to 15 JVM. Each JVM is binding with 1 Numa. We get the TPS is up to 1200. The CPU utilization is around 70%, both on the application server and database server. So this is the best result we get from for this POC. So is there anything we can improve for this performance? Then we look at the database time. We can see that 20% of the database time is spent on the compile secure phase. Compile secure phase is to generate execution plan for secure statement. Why TiDB spend so much time to compile the query statement? We then look at the TiDB CPU profile. 18% of TiDB CPU is spent for compile prepare statement, and 36 memory object allocation is also for the compile secure phase. Why? If we look at the metric, the plan cache hit OPS is 33,000 per second, and we got 46,000 execution per second. So the plan cache hit ratio is 72%. Without hitting the plan cache, it means that we need to repass and re-optimize for every single execution. And the percent is not 100%, is because in the version 5.1, TiDB some kinds of the secure statement can use the plan cache. There is no limitations. So the high compile CPU and memory cost, they have a negative impact on the GoLang GC and the query performance. We can pull a trace for one of the TiDB, and we can see for the same secure statement, and the query latency range from 1.5 millisecond to 15 millisecond. So if we explore the stall execution, the go routine need the go routine store and switch to the GC work, which is the green execution. Why the go routine, which execute the secure statement, is need to store and doing GC work? Because there's a high memory and a high object allocation in the database, so you need to do the GC. So in the later version, like in the 5.3, there's a plain cache enhancement. The same workload, running the same workload, it just has 7% of database time is on the compile secure phase, and the plain cache hit ratio is almost 100%. So this is a demo that TiDB in the new version, we are improving the plain cache to reduce the CPU and memory cost, and to improve the query stability. The other case I want to share is that the plan stability change. This is the query that has two execution plan. One is 62 milliseconds, one is 38 seconds. It's a huge difference. And if you look at the TiDB dashboard, we can see there's a two execution plan for the secure statement, which access the MQ producer message table. The predicate is a flow ID and the status, and for both flow ID and status are indexed. So we know that the flow ID, maybe we should use the index on the flow ID, right? This seems the column seems very distinct. For the long execution plan, we see that the optimized things that the status equal 1. There's 0, the cardinality is 0 for the status equal 1 predicate. So the status index is used. So this causes the long index. Why? This is a case we call always there status. The reason is that MQ producer message table is a message queuing table. During the workload, there's a small number of data with status equal 1, which is the new message to be processed. After the workload, all the message processed and no data with status equal 1. So just before the benchmark, auto analyze is triggered, and there's the no status equal 1 data. The new gather status calls the long estimation and the long index. So this can be confirmed by the updated time on the state histogram view, which indicate the last analyzed time. So we submit a multiple optimizer enhancement. For example, the optimizer need to support locking the status to avoid the unrepresentative status. So to solve this kind of issue, quickly on production system, status also need to store the history status version. So when there is similar issue happen on production system, the DBA can revert to the previous good status version. Okay, the key takeaway of this talk is that on the ARM servers, everything should be binding with Numa. The JVM, the HAProxy, the PD, the TiDB, Takeways, everything should be binding with Numa. And the core question for performance tuning is where goes the response time, and how to get a full picture and identify the bottleneck. What we propose is tuning by DB time. So you can get the database time from TiDB dashboard, the Grafana performance overview dashboard. We also use various tools like Flame Graph, Performance Top, MP State, GoLang Trace, and the Profile to help us to do performance analysis. This is the key takeaways. And actually, TiDB is keep improving for mission critical OLTP. For example, in the 5.3 version, we create the plan catch, and for this core banking workload, the plan catch ratio is 100%. In the 5.4 version, we improved the Takeways write performance by introducing async IO and log engine. In the version 6, we introduced small table cache. So some of the read heavy and small table can be cached at the TiDB side, and we also improve the permissive log to make it in memory. Okay, this is all the topic, and question is welcome.